pH. What the heck really is it? And what's the deal with the number 7? So pH is one of those concepts that it can often get really confusing if you actually want to understand what's really going on. And so normally if you ask someone what pH is, they'll say, oh, it's a measure of how acidic or basic a solution is. And then you're like, okay, well, what does that mean? Where does it come from, all of this stuff? And then you get well, the mathematical definition, pH is the inverse log of 1 over the concentration of protons. Okay, and where does that come from? And it can be kind of confusing. And so I thought I'd do a post on pH, and where these numbers come from, and how to interpret them, and really think about what's going on inside of a solution. And yeah, so thinking a lot about PhD, so I thought I'd talk about pH.
So we normally think of water as just like H2O, right? So you have 2 hydrogens attached to an oxygen. But actually, water is like a mixture, because water can actually auto-ionize. So an ion is a charged particle, and water can dissociate. It can actually lose one of those hydrogens and leave the electron behind. So you lose that hydrogen as a proton. And this usually links up with another water molecule to give you a hydronium ion. So you're left with the hydroxide ion, so the water without that proton, and then a hydronium ion, so the water with that proton, or just the proton free floating, but they're normally just an electron to one of the other waters to form this hydronium ion. However, the amount of this is happening is very, very low compared to this amount of the water. So we can think of having an endless water fountain. And there's a mixture that water is happiest with, and this is going to be the source of the pH. So when I talk about a happy place, talking about thermodynamics, so at equilibrium, what is the mixture that water wants to get to? So how many protons and is it one? What combination of protons and hydroxide ions will make it happiest? And so we call this water. We have this water equilibrium constant, or Kw. So water can constantly be, so these, in addition to joining up with another water molecule to form the hydronium ion, this proton can also link up with the hydroxide ion and give you back water. So you can go both directions, and at equilibrium, so if you give it long enough and you don't disrupt the system at all, you'd reach a perfect happy place. And this is represented by this water equilibrium constant, or Kw. So Kw is the concentration of, so these brackets being concentration of, the hydroxide ions and the proton ions. And the concentrations here are in molarity. And so going back to molarity is just the unit of concentration that's equal to the number of somethings per liter, the number of moles of something per liter. And so a mole is it's kind of like the biochemical dozen. So it's 6.02 times 10 to the 23rd. So it's a ton of stuff, but molecules are really, really, really tiny. So we need these numbers to help us describe a lot of things in numbers that aren't super, super giant. So if we go back to our idea about this water equilibrium constant, so this is the happy place that water wants to get to. And so when we have these concentrations, so even though we're in molar, we're still in really, really tiny values, so 1 times 10 to the 9 - 7. And so what happens is when you multiply, so right here we're multiplying these exponents, you add them, and so now you have Kw equals 1 times 10 to the minus 14. And so water is always going to get to this happy place where 1 times 10 to the minus 14 equals the concentration of the hydroxide ions times the protons. And So then if some of that hydrogen gets taken by an acid or a base, gets taken by a base, so a base is something that takes protons, or an acid, something that donates protons, so if an acid adds them in there, then the solution can draw from this endless water fountain to help get back to its happy place. And the pH is like a measure of the amount of the protons that are there when water gets back to that happy place. And so if you have a high pH, we call that like a basic or alkaline condition, and you have more of this hydroxide than the protons. At a neutral pH, we have an equal amount, and then at a low pH, you'd have more of the protons and the hydroxide ions. And so where does this like 7 come from? This 7 is as neutral. So going back to our idea of this like water equilibrium constant. Well, it's nicer to be able to work with exponents. It's nicer not to have to work with exponents. So we can get away from the exponents if we take the negative log 10 of these things. So if we do this, this will turn into addition. We're multiplying here, but remember that when we multiply exponents, we're adding this like exponents. And then if we take the negative log, what we end up getting is 14 equals the negative log 10 of OH minus, and then negative log 10 of OH minus. And so we just abbreviate these pH and POH. And then if we shuffle these around a little, we see that the pH equals 14 minus the POH. And so the disadvantage of doing this logging is that now we have bigger numbers correspond to smaller amounts of protons. And so when we have a high pH, that's actually like a basic or acidic solution. A basic or alkaline solution. Whereas we have a low pH, that's an acidic solution, so you have a lot of protons. And so the more protons there are, the lower the pH. And the reason why we have that 7 is because in a neutral, so we remember that like in a neutral something, you have to have an equal number of minus and plus. And with water, if you had a pure solution of water, no other acids or bases added, then the concentration of your protons has to equal the concentration of your hydroxide ions in order to be neutral. And since we have to be getting to 14, then each of those has to be 7. And so by 7, remember that then if you take the opposite of the negative log 10, then you get back to having 1 times 10 to the negative 7 of each. And the negative log of that is 7. So this is why neutral water has a pH of 7. And so if we say that we have an acidic solution, that means you have lower than 7, and if it's basic or alkaline, it's higher than 7. But how do you get to those values is by adding an acid or a base. So this is pure water. We have the 7. But what happens is water is always going to want to get back to that happy place, remember. So it really wants to get to this happy place. And so what happens is that if you add an acid or a base, the water is going to have to compensate. But remember that water has this giant fountain of like endless water, this endless water fountain that it can draw from if it needs to. It has this endless fountain that it can donate from. So what happens is that if you add an acid, so an acid remember donates protons. So if you add an acid, now you're taking the water away from its happy place. And so some of the protons that the acid is donating are going to join up with this OH to make water, and they'll just add a drop in that water fountain. So we don't really have to worry about that too much. It's just remember it's an endless fountain of water because there's so much more than normal water than the ion forms. So this is going to shrink your free OH a little as well, but it gives water back to the state where you're at this happy place, this 1 times 10 to the minus 14. If you do the opposite, so add a base, so that's a proton stealer, then it's going to take protons. The water is still not in its happy place. the water gives up, this neutral water gives up more of its H plus from its endless fountain. You also generate a little more OH minus as you do this, but what you care about is that combined concentrations and getting to that 1 times 10 to the minus 14. So you still get back to a happy place, but now you're in a happy place where you have more hydroxide ions than protons, and so now you have a higher pH. And in this case, you would have a lower pH. And so this is how adding acids and bases can alter the pH of a solution. We can actually go back and forth. So if you have like in a mixture with just water, so water is kind of acting as its own as an acid and a base, but you can add additional acids or bases, and that's how you can like change the pH. And we can actually know how much the pH will change with this like Henderson-Hasselbalch equation, which gives you a way to go back and forth between the pH and the pKa, which is a measure of how strong an acid or a base is. And this will get you the pH change that you would expect if you added like a certain amount of an acid or a base. So basically, the pKa, so the pH is a measure at the solution level, whereas the pKa is a measure of the strength of an individual acid or a base. And so I'll probably do another post on that to explain. One more thing before I go is, so one thing that always confused me is like, how is it that like protons can just like fly in out of anywhere and like the equations and stuff are just always there? Well, remember we saw that water is kind of like that endless fountain. And so by proton, remember, so elements are made up, atoms are made up of like protons, neutrons, and electrons. And so the protons, the number of protons defines the element. So hydrogen's always going to have a single proton. And hydrogen only has one electron. And the common form of water doesn't actually have any neutrons. And so this means that the hydrogen, if you take away that electron, it's still hydrogen because it has one proton. But that's all it has. So it's a proton. And it turns out that so atoms join up to form molecules by sharing pairs of electrons to form covalent bonds. So remember, we kind of talked about this as like dog walkers. And so the protons, like they're positively charged, they kind of have this leash, they're reining in those negatively charged electrons. And some elements have like stronger dog walkers, so they have a stronger ability to rein in those electrons, those negatively charged electrons. So oxygen's really good at reining them in. Hydrogen, not so much. So hydrogen, it only has that one proton trying to like rein in that electron, and the electron's really energetic, and so it's going to hang out more with oxygen, which has a stronger pull. And so it's easy for the hydrogen to leave, but when it leaves behind that electron. And so this is why you have this ionization of water where that proton can kind of leave more easily. So most covalent bonds are stronger than this, but because hydrogen is really bad at holding on to that electron, and oxygen is really good at holding on to electrons, the hydrogen can leave more readily. But just how readily it can leave depends on something called the pKa. And so that's a measure of the acid strength.